Okay, thank you. My name is Grzegorz Piwowarek, and yes, I do write Java code, but I consider myself an engineer, a kind of post-language kind of engineer, so I tend to focus on solving business problems with the tools that are the best for that, not necessarily with Java, because that's like one of my main languages. And for example, I write full-time Go since like 5 months already. I've done some Kotlin, I've done C# in the past, I've done TypeScript, but yeah, if you ask me, Java is like one of my personal favorites, at least in the context of what I do love the most, which is like backend engineering distributed systems, especially those that have tight non-functional requirements. So I've been around for a very long time in the IT industry. I started very early, but unlike most of you probably, I started with 3D graphics. And at some point when I tried to animate a fire, and as you can imagine, that's like animating thousands of small images, rotating them and snapshotting every frame, and there's like 30 frames per second or so. So as you can see, this can be kind of tedious. And then I realized, well, you can automate that. And I'm like, so are you telling me that I spent 3 days moving all those sprites manually, only this can be done with just a couple of lines of code? Yeah, so that's how I started. And yes, I've been mostly in the Java space, but for a very long time I am focusing on fixing business problems, especially in the field of performance, distributed systems, and microservices as well. And the whole reason why this presentation exists, and I don't know how it's been in the Ruby space, but in Java space, microservices were a very hot thing 10 years ago. And there's this guy still speaking about those now. But the thing is, when I visit companies, when I deliver workshops and I consult, people make the same problems all over again. It's like, those are the same issues that I've seen 10 years ago. If I go on a workshop right now, people are having the same damn issues. So that's why this presentation was born, and I identified a few of them that are kind of most common, and we'll go through those. And I will try to make them a bit more interesting than, oh, you forgot about observability, oh, you forgot about CI/CD. Okay, that gets hopefully a bit more interesting. So yeah, that's kind of true if you think about it as well. We as an industry, we shouldn't make those mistakes anymore. I do a bit of blogging, I do workshops, consultings, but most recently I'm one of the first engineers at Warsaw tech startup Quezma. What we are trying to do is trying to invent a new type of infrastructure. We call it database gateway, so we want to permanently put stuff between services and databases. And this is just a couple of us, so we focus on a very, very narrow space. We don't want to do in the long run, but it turns out to be a very good bet at the beginning, because there are companies willing, if they are experiencing the same problem, they are willing to talk to us, even if all we could show them was just slides. And we focused on interoperability between ClickHouse and Elasticsearch. If you have Elasticsearch cluster at scale, you are likely to experience a set of problems that we can solve. And if you have those problems, you are very desperate to get them solved. But that's just us having a bunch of slides. Anyway, so microservices have been around for a very long time. But we keep making the same mistakes all over again. And why is that? I have no clue, but I have some ideas. So the first thing is that I believe most companies didn't, yeah, that's an obligatory slide. Most migrations into microservices I've seen were, let's say, naive. So there's a bunch of eager people trying to, okay, let's do this because that's new, that's modern, that's better, because monoliths are bad, microservices are good, let's do that. And they split very eagerly everywhere. Okay, just split those stuff into smaller pieces, and then you end up with just a bunch of crap, just a bunch of smaller craps, not one big crap. but still crap nonetheless. We as an industry became very good at coming up with new tech that's supposed to compensate for the problems in design. So okay, we failed the design. Now we have distributed crap monolith, but okay, let's apply service mesh on top of that and other stuff. But guess what? That's still an afterthought that won't fix your design. So let's go back a couple of years, like 60. There's this guy over there, Tony Hoare, that invented null reference. So I don't know how it looks like in Ruby, but in Java, when you call something on null, you get a null pointer exception. And that guy is responsible for that. Because if he hadn't invented this, that's how the world should have looked like. But guess what? It's there. Now this guy needs to live with a dilemma which is comparable to Oppenheimer's. But yeah, that's because he thought, well, let's use a null reference for that. And I do believe that in the future we might be speaking about another billion-dollar mistake. And that billion-dollar mistake is microservices. But don't get me wrong, not the concept itself, because the concept has been around for a very long time. It had different names, you would implement it slightly different, but like service-oriented architecture, it's essentially the same if you think about it. So that's not totally new stuff. But that micro in the name was very confusing for a lot of people. And that sparkled a lot of size obsession. So if we have service-oriented architecture and we have microservices, well, what's the difference between a service and a microservice? Because it's clearly not the same thing. The services, we've had services that service-oriented architecture, but now we have the new thing, and there are microservices. What's the difference? And so, how small is micro? Is it 20,000 lines of code? Is it 100 lines of code? Is it small enough or not? So how do we measure that? Number of lines of code, number of classes, megabytes, how big the deployable is. And as you can see, all those metrics do kind of suck because they don't capture the essence of the functionality that's included in that's being served by a particular service. I think one of the best metrics I've seen that do work is a service rewritable in a certain amount of time? That obviously is very contextual because it varies per technology, per team, and so on, and per circumstances in a certain company. But it's a bit better than the service turns into microservice at 17,354 lines. Also, if there are microservices and services, it doesn't imply that nanoservices exist. What's the perfect size of a nanoservice? I don't know. To answer that question, I will try to answer this question later on. But let's recall the main idea of microservices. And that was to enable scalability through independence and modularity. But when I say scalability, that's not necessarily just driving the numbers of requests per second up. Scalability on many different fields. For example, organizational scalability, or how many people can work on a single system. Think about this. You have one person team. That person is tasked with delivering something. That person works with zero process, zero code reviews or anything. They are happily committing and pushing stuff to the main repository. If that person is, let's say, working fine and is not interrupted, we are likely to get 100% of utilization of that person. So they are working at the optimum, delivering stuff as fast as possible. But perhaps that's not enough. You need to throw another person into the team. But now they need to sync on stuff. Sometimes they might work on conflicting pieces of code. They might need to discuss some stuff. They need to be managed. So if you put a second person into the team, that's unlikely. So the throughput you get is unlikely to be 2 times, the output or the maximum possible output of one single person. And then you keep adding more and more people, and suddenly you have you see that this doesn't scale at all. I mean, this scales, but not linearly. Or even worse, it might be becoming worse. So you keep adding more people, and the total throughput is lower than it used to be. So what can we do to make this work in somehow? So the original idea was to modularize the system in order to leverage low coupling and high cohesion. So if we think about monoliths and their structure and what makes you call them a big ball of mud, it's essentially the fact that you have a system where concerns are not separated, where functionality is intertwined between each other. So imagine that those red dots represent functionality responsible for ordering movies or like renting movies. Even the yellow one might be functionality responsible for account management. Those green, turquoise, bluish ones might represent, warehouse management system. Because guess what? Those are like old school physical copies of movies that might be rented. And now you throw 50 people on that, and now there are problems. And the problem is that if you want to refactor something, you need to, let's say you want to change only the movie renting part. But this is here. And this has arrows to the warehouse part, which has dots to the account management part, and so on and so on. And the more the arrows you have, the more time you need to spend on cutting them and stitching them back together when you make some changes. And this is what makes software unpredictable. I mean, function is unpredictable to deliver. Because at the beginning, when it's small and easy, okay, you know everything, and it's predictable, you can say, I'm tasking you with moving that button, 2 pixels right, and I'm saying, okay, that's easy, I can do it in 5 minutes. But suddenly, if you have a way bigger system where everything is intertwined, well, that might be anything between 5 minutes to 2 months. Who knows? So the solution to that is easy. Let's modularize that system. And the way it looks like is that we take what we had and we try to identify public APIs of every functionality and make those modules talk to themselves only through those public APIs. Through, rigid, static, predictable, backward compatible public API contracts. And this might not look like a big change, but look, as long as the communication happens at the public API level, I am free to do whatever I want inside this functionality, this and that. I can cut off all those errors, but I don't impact other errors as long as I'm adhering to the public API contract. So I'm able to refactor, redo it totally with no impact on the other parts of the system. And by modularizing the system, what you can effectively do is to get closer to that perfect original state where there was just a couple of developers working happily on stuff their own. And this is an attempt to bring it back. So you had one big system with 50 developers, but let's make it easy, let's make it 30. You modularize this, you give them ownership on the smaller pieces of the domain. You make them communicate with other using established contracts, and you give them freedom. So now you have bigger system consisting of 3 smaller systems, and there's every team knows only their part of the domain. But they don't need to know everything, they just need to know a single part. And they can release every month, every day, whatever, as long as public contract is satisfied, others shouldn't care, and so on and so on. And that's the original main idea. That's why microservices should be considered mostly by big companies that are facing scalability at organizational level. So you don't necessarily need microservices if you want to drive your RPS numbers up. But if you want to throw more people onto a system and make them not kill each other, that's the original idea. So, but the thing is, you can have all of that, I mean, part of that, even if you don't do microservices. Because, well, forgive me, those are examples of Java, but this should be very easy because that's how deep are we going to get into Java. What's common in the Java world is that when you structure your application, at least packages, and packages in Java are not hierarchical. So If you have com.piwowarek package, account rental warehouse, there is not hierarchy, or they are all separate. So com.piwowarek is not the super package of com.piwowarek account, and so on. And what most people do is they, and I don't know why, they will create a package called infrastructure, DTOs, services, repositories, and so on, which are very layer focused. And this is very problematic because it forces all your stuff to be public. All your classes will be public. So if you are in the developing an account module, there's nothing stopping you in, touching some repositories of the warehouse module, which are their implementation detail and shouldn't be touched at all. But there's nothing in the language that can stop you from doing this. Obviously, there are tricks that you can use to ensure this modularity, but generally it's a problem. But if you rethink the package structure, that's where you can get some of those benefits. Obviously, you can deploy account module separately from rental module because it's a single application still. But you already have certain benefits when it comes to maintainability. Because as long as those modules have rigidly defined public APIs and they communicate using those public APIs, you are free to do whatever you want inside the module. You can rewrite those fully, you can replace your persistence framework and so on, and that shouldn't impact other modules. So here's the thing. In most cases, when you're starting with building a new system, in most cases you don't want to start here. Because usually the team is small, probably you don't have customers that are paying a lot of money. So there is really no point in investing so much money and time into building infrastructure for supporting all of that if there's just a couple of you working on a single system. If you want, the natural path of evolution is that you start with a monolith, and once you feel some pain, that's when you evolve into microservices, slowly, one by one. If you want to do some engineering, well, let's not call it premature engineering, but let's some smart engineering up front, you might want to start with that. Because the cost of building a modular monolith is, like 10% or less than 10% of investing into building proper infrastructure for microservices. And it's way easier to maintain, and why, you will see in a second. But anyway, the point is that Sam Newman, the author of the original microservices book, says that the smaller the service, the more you maximize the benefits and downsides of microservice architecture. But guess what? The smaller the service, those are not linear. Those are not linear changes. So there is a point where you start experiencing diminishing returns when it comes to benefits you get, but the downsides, they start to pile up and it starts becoming painful. But usually someone comes and says, okay, but let's look at the architecture of Netflix. That's how they build it, and it works for them. Guess what? But there is one very important contextual detail. Netflix has 2,000 engineers. Now probably a bit less, since they fired quite a lot of them. But the thing is, Netflix has been around for a very long time. And that architecture didn't happen because they took the smartest people they had in Netflix, closed them in the basement, for a month, and they came out and they said, Eureka, we have it. We need exactly 2,172 microservices, those are their names, and they gave that diagram. That's something that evolved organically into this after many, many, many years. But there are a few interesting plot twists here, because not a long time ago, Paul Baker from Netflix released a very interesting article. But anyway, in most cases, if you are trying to copy and paste practices from very big companies, obviously they have very good ideas, but you need to make sure that those are applicable to your context as well. Because if not, that's what you might end up with. And here comes the snippet from interview with Paul Baker, one of the most important engineers at Netflix. So yes, they have microservices, they have thousands of them. But guess what? Some of those microservices are a lot larger than most big monoliths that he's seen in many other companies. Well, how can size of a microservice be bigger than those big ball of mud that they've seen in other companies? How could that be? Because that's the point. Really the size of a microservice doesn't really matter. If you go back to this diagram, it's more about separating, building those independent, giving modularity and independence of evolution of certain modules to bring the situation back to this perfect state where there's just one developer working on their stuff. Obviously, usually that's more than one, but that's the perfect state. So here comes the point. If you came here for me to tell you where's the moment where you split, how many lines of code, that's a really good question to ask. If you've heard about domain-driven design, there's a way to come up with the optimal setup, but that usually involves bringing some domain-driven design experts, organizing event storming sessions, organizing events, trying to figure out domains and new boundaries, and that gets you to something very close to optimal split. But guess what? That takes a lot of time to teach, and I have just a couple of minutes. So let me show you an approach that works really, really well and can be taught in just a couple of minutes. So the thing is, it's not about structure and lines of code, but when do we split? And that's very easy. When we start experiencing pain and it hurts too much. If this is a small pain, okay, maybe we can live with that for some time. But there are situations when it hurts really much, and if it's unbearable, or we are anticipating that it will get unbearable, very quick soon, that's when we split. But guess what? We don't split, suddenly, we had one big ball of mud, and we don't do this immediately, but we split in 2, 3, slowly, one by one. And that's how you can organically evolve your architecture into something that's likely to support you and address problems that you had. Because there was something painful, you made a change, gradual change, and you either get better or worse. If it gets worse, you roll back. If it gets better, okay, you observe, you evaluate, and potentially do it again. And believe me, in most cases, you want to delay going into the world of microservices as much as possible for a very simple reason. If you go from one service to two, this is no longer a single service. Now there are two services communicating over a communication channel that's unreliable. Messages might not arrive, messages might get dropped. Suddenly you need to start thinking about high availability, consistency, policies of distributed computing, or distributed transactions, and that you normally don't need to. So if you don't need this, don't do that. You will be much better, much more happy. And when it hurts too much, going into world of distributed systems might actually be an okay trade-off. Well, you need to manage suddenly eventual consistency, deal with unreliable communication channels, but well, you got your organizational scalability because now you did grow. Now you have 500 people working on your system. Well, there are problems associated with that, but the trade-offs, let's say, were worth it. So there's this guy, DHH, and he describes a very nice pattern. He calls it majestic monolith. So in most cases, when you jump into a, let's say, average, maybe like statistically average company, that's neither a big and established one or a startup that starts, in most cases, what I would expect to see, is something that would tell me, okay, they are organically growing their architecture in a good way, is that they don't have this huge, this Ebola-like virus looking, like coronavirus looking like architecture, but they have probably a couple of huge monoliths in the center with a couple of small, auxiliary services all around the place. That kind of tells me that they are taking the evolutionary approach and they're making the cuts when this is actually needed, and not because they figure out, okay, we had one big monolith, let's put it into 200 services at once. And believe me, the point where you really need to go into microservices is quite probably further away than you think. So There's a blog post from Instagram engineering, and there are actually two blog posts. One is saying that pretty much how Instagram is running on a one big monolith. And when Instagram was launching threads as well, what they did is they copied and pasted pretty much the whole thing, and this is also running on a monolith. So if Instagram can get away with working on one huge monolith, it means that the point where you really need to migrate is further than you think. Okay, but we've migrated because, well, we were really forced to. But here comes another problem. The problem is that all habits die hard. So what I often see is that the company committed to evolving into microservices, but they don't really want to let go some of the things they were used to. So that usually starts that you have one repository. You split the service. So now you have 2 or 3 in the same repository. So guess what? You apply the single versioning to all of them. Because in Git it's very easy. It's actually quite complex to have different tags per directory. It's very easy to have a global tag per repository. So you have one repository, you have one global tag, and you have one single version for all the services. And where's an independence in that? Well, there is not. And if you have one single version of services, what follows is that then you often want to have all or nothing deployments. So someone says, okay, let's deploy all of those at once. So we have a new version of our system, like 2.1.0, and let's release everything. Not just a single thing, but everything at once. But if you can't release things independently, you lose most of the organizational scalability, because now you need to reach an agreement, sync with other teams, and figure out when is the optimal point for everyone to just freeze and release everything at once. And usually something doesn't work, and that's painful. That's not where you get the benefits. If you want to commit to microservices, you want to embrace independence. You want to let everyone version when it's convenient for them, release when it's convenient for them. And if you didn't slash your system, randomly, this will be fine, because every service constitutes a different functionality. So if you are one team working on renting movies, you shouldn't probably care about, other folks responsible for implementing and maintaining functionality related to physical management of movie copies in a warehouse. So let me tell you a story. Some time ago, not a long time ago actually, I was the lead engineer for Hazelcast. I'm not sure how this technology is known in the Ruby world, but it's a distributed in-memory platform, very known in the Java world. C#, Python, not sure if Ruby, we never had a Ruby client. But anyway, at some point in time, I was asked to do an internal audit on the cloud product. Our previous VP of engineering felt like something is off there, something is going wrong. So I heard that team has a lot of microservices, but they do release every 4 or 5 months. And the irony of that is that the core product of Hazelcast was a Java package, like Java jar file. And if you give someone a jar file with public APIs that people compile against, that's as restrictive as it gets when it comes to maintaining backward compatibility. It would be very, very delicate when it comes to making any changes. And since this is a very important piece of infrastructure used by multiple clients, you need to be very, very careful about making changes to the whole thing. So this is as painful as it gets to release. And for some reason, the team that had 68 microservices was able to release slower than the core team working on the database-like product itself. That's at least weird at least. So I was asked by previous VP of engineering to go and do an internal audit to look at that. And yes, there was quite a lot of over-engineering there, but the biggest problems were caused by the old habits. They all tried to apply single versioning. They all tried to do all or nothing deployments. They always try to sync and make sure that they're in the perfect spot to release the whole thing at once. But it was never there. So they ended up postponing releases, testing again, to the point where it will take 4 or 5 months to release a new version, which was absurd. But when it comes to the architecture itself, there's a funny part. They were afraid, when I went there, they looked like they were afraid of me. So when I was asking questions like, okay, so how big is the traffic, or how many customers do you have? The answer was 1, and I'm like, okay, but 1, like 1,000, 10,000, 1 million, how many customers do you have? No, 1, like 1 customer. And they don't pay because they are at the POC stage. Okay, so you build 68 microservices with 1 customer. And then they felt like they got afraid. It's like, no, Grzegorz, don't worry. Yes, we did 68 microservices, but we are planning to do 150. We have already planned 100 more. And like, don't fire us. We will add 100 more. Like, you see, this will be perfect architecture with 100. Like, that's not the point. They felt like they really need to produce a lot of very small ones for me to tell them, okay, that's really good for 1 non-paying customer. But the thing is that was quite the opposite. That system would be fine with 4 or 5. But the system was heavily cloud native, so actually we would benefit from having a couple of separate components. But again, they totally missed the point. Another thing, the classic stuff. Dedicated DevOps bottleneck teams. So you have a couple of teams, you want to release stuff, but you got stuck with the ops-like mindset. So there is this team of people, they are working separately with the product teams, and they are tasked with ensuring that releases are safe, secure, and stable. Guess what? What's the main opponent of secure and stable and safe? It's a change. Change is the main enemy. And so there are those developers that want to release and develop new stuff as soon as possible. And in the world of microservices, this can mean multiple releases per day. Because if service is small, you can release it quite often, with confidence. So what I've seen, the classic archetype is that there will be a class war between them. Because developers will want to ship, and the ops team, which is on call every night, they don't want to ship their stuff because stuff can change and they get punished for that. So if they let stuff into production that doesn't work, they get punished twice, because they get punished for not doing their work, and secondly, they get called at 3 AM to fix stuff they didn't do by themselves, because that's those damn developers that didn't test their code properly, right? So Google actually did write a couple nice book about that. It's called how it's called? SRE, Software Reliability Engineering. And they have the whole section dedicated to the problem that they faced at Google, which was the same, and how they try to tackle it, essentially by merging those roles together and making sure that those people with ops responsibilities are part of product teams. And that's usually the solution. You want DevOps, like those ops profile people, to be part of the product teams. You want to make sure that their responsibility is the same as the product team. You want that ops person to consider their failure when the product team can't ship new functionality, say. And this ensures kind of that there won't be this clash when ops say, okay, just keep testing it for a month, I don't care. I don't get paid for releasing new functionality, I get paid for making sure that nothing breaks. Another thing is, when you delve into the world of distributed systems, at some point you need to stop thinking that you can end-to-end test everything. If there's one service, okay. 5, okay. But there is a point where the scale is too big, like think Allegro or eBay or Netflix. Imagine you change one very tiny component responsible, I don't know, for displaying logs or sending Slack messages. And then you trigger this huge suite of tests that run for a couple of hours because you need to test the whole system at once. This doesn't scale really well. So at some point you just need to let it go, and you try to think about how to compensate for that. Obviously you need to test services individually. You can test contracts and between various services. I'm not sure how you do that in Ruby. In Java world, The tool that's mostly language agnostic is called PLRUG. It has its downsides, but does the trick somehow. Obviously, you can have some of those tests running continuously on production. You can have black box tests, which I like personally a lot. So that's what you would call when you take your deployable, for example, Docker container, you run it, you stop all the other integrations, like Kafka's databases, and you run those tests, and those obviously you adhere to the testing pyramid, but this allows you to ensure that deployable you've built at least runs and integrates well with the rest. And the common issue I've seen is that all the tests run, integration tests run, but hey, you ship it and the Docker container doesn't start because of some dumb misconfiguration. And that also works pretty fine. Anyway, the topic of testing is very difficult and deserves way more time. So at this point, I just want to signal that probably at some point, you won't be able to make it if you want to end-to-end test everything. Just imagine, 20 teams, they all ship at once, there is one environment, and the test suite runs an hour. So if the test suite is running, and the second team is deploying a new version of the service, should I restart my test or no? Maybe it creates 20 different environments for every team. No, not ideal, because you don't test together all of that, right? So someone at some point figures out, okay, let's have one environment, but let's have a big pessimistic lock on that. And just let's queue those jobs to ensure that every change is tested with the newest possible versions of other services. Doesn't scale at all. Terrible idea. And again, even some human original microservices book says, from author on the original microservices book says that if you can't make a change to a service and deploy it individually, then probably you are just paying the price and not getting much value from microservices. Because this is where it really shines, where you can make and deploy things independently, when every team can make a change without informing others. Another hard, difficult, religious topic is monorepos versus repos per service. And I've seen both work fine, but I have one clear preference. And that preference is that repository per service. Why? Monorepos make it very, very easy to stick to the old habit. Because guess what? Now we have 20 services in one repository. Obviously, it's very easy to tag all of them at once, build them all at once, release them all at once, because that's probably not just a script that goes through all the modules and just releases them one by one. But what's even worse is that you can make distributed atomic changes to multiple services at once. Because, well, guess what? Git allows you to. Because you have two directories, you make changes, backward incompatible changes to both of them. And you commit, and it works. But guess what? Then you need to synchronize your releases. So then you call your ops people, you say, okay, well, this service is already going for CI, it's going to be up very soon, please stop it, and make sure that this second one goes first, and so on. And you go back to the setup where you again need to release multiple things at once. And that sucks for the same reasons why releasing everything at once sucked. So if you want to do monorepos, it requires a lot of extra tooling and a lot of extra discipline. Because you need to make sure that you don't make backward incompatible changes to multiple services at once. That would force you to make a synchronized deployment. But you also need to build quite a lot of extra tooling. You need to build tooling that manages to tag and version every directory separately, release every directory separately, and you need to figure out how to build those separately, because probably you don't want to build all your 200 services when there is a change in the README. So you need to figure out some diff management, identify, okay, those changes are from this service, so I'm building only this service and preparing a new version of that. That's something you need to create and build. If you are starting with repo per service, that's super easy. If you are working with Jenkins or GitHub Actions, you just create a file. Jenkins can automatically identify new repository in the organization and immediately create pipelines for that. And you can have a template in GitHub of the repository, you just create a new one and automatically everything starts to working. That's super easy. So I would advocate you start doing repos per service because it might be a bit more inconvenient for a developer to manage multiple repositories, but it's worth it because you make it very hard to do some illegal stuff like this. Distributed transaction commits to different services. Plus, modern IDEs, at least from JetBrains, they have no problems adding multiple source sets into one single view. So, despite having multiple repositories, those can still feel like monorepo in your IDE. So, another classic, not embracing eventual consistency. So, okay, we went into the world of microservices. We have 150 services. And so now they all need to be up and running at the same time for the whole system to work. One service collapses and your system doesn't work. That's not how it's supposed to be. I mean, we wanted to split the system into smaller parts so that the opposite happens. So that 20 services can go down, but other functionalities of the system can work normally. But in order to make this happen, you need to start thinking about trade-offs between synchronous and asynchronous communication. And if you listen to microservices experts or advocates, they will often tell you, okay, you need to have async communication because that's how it's supposed to do, that's how it's supposed to be. I would call that untrue. In most systems, there's a place for synchronous and asynchronous communication. I'll tell you default to synchronous communication and apply asynchronous when you really feel it, when you need it, because guess what, that's way more work. And the reason for this dilemma to exist is that in the world of distributed systems, we need to make a choice. Do we want to stay consistent or do we want to stay available? What's most preferable? In most cases, you want to bet on availability with small areas of the system where you need to be 100% strict consistent all of the time. And the reason for that is very simple. If you have two nodes carrying values, and they need to agree on a single value and say, okay, do we both carry the same value? They need to have communication channel. And if that communication channel is unreliable, they can't give the right answer. So imagine you are going on a party with a friend, you see that there's a communication channel established, you see that that person is here. Maybe this person went somewhere else, but you still you can phone them and ask, wait, where are you? I'm by the bar. Okay, fine, I guess. But guess what? So now, the wife of your colleague calls you and says, I can't really get to my husband. Can you tell me where he is? And you look, you call him and say, okay, he's by the bar. Okay, fine, yeah. You are consistent and available because you've given an answer. And you gave your answer, which is up to date. As up to date as possible. Because you see that the guy is here, clearly by the bar, so you say, okay, he's by the bar, right? But now, imagine that this guy's phone dies. So the wife's calling you, where's my husband? And you can't see him, and you call him, and you can't reach him. So network partitioning happened, and what can you say? You can either choose to stay consistent or available. If you want to stay available, you want to say, okay, he's by the bar, because that's the last time when I saw him. But if you want to stay consistent, you just say you don't know or you don't answer at all. And that's the big problem that you have when you communicate, when you replace your static method dispatch with network calls. Anyway, if you want to be fully independent, you need to forget about string consistency in the world of distributed systems. At some point, you will always need to have with some eventual consistency to deal with. So, what's synchronous communication? Well, you have two services, you call it HTTP GET, give me your account number or so. Give me a list of orders or something. And you get it. That's synchronous. But when the service second dies, you can't really ask for the list of orders or something because the service is down and you can't perform your functionality. And that's where you prefer consistency over availability. You can't really serve a functionality because there is no communication with some other service. So what can you do in such case if you want to gain extra bits of availability? You reverse the error. So instead of having service 1 ask service 2 for data, you make service 2 communicate with the rest of the announce changes. So service 2 can announce changes that happen. For example, a new order was created. So instead of replying with a whole list of orders, you say, you emit an event that goes for Kafka or RabbitMQ, whatever, and other services are listening for that. And it's like, okay, I got a new order, and I can update my local projection. That projection can be, database entry, this can be purely in memory, this can be somewhere, whatever you want. Anyway, but you keep it locally. So you create redundancy when it comes to your data, which is not a bad thing by itself, but for the price of redundancy, the price of higher availability is redundancy. So you keep redundant data, but now if the service dies, service 1 can answer, can perform its functionality, but guess what? It's staying eventually consistent. It doesn't give you guarantees that it responds with the most up-to-date data. In most cases, that will be, because that's like these events are likely to travel from service to service 1, in hundreds of milliseconds maybe. But something can go wrong, and these hundreds of milliseconds can turn into days or years potentially, because guess what? A couple of years of delay is okay in the world of eventual consistency. But guess what? Eventual consistency is not accidental consistency. And it's another very common pattern that when I jump into systems and I see, folks, you don't have eventual consistency, you have accidental consistency guarantees, or you permanent inconsistency guarantees. Let's take a look at this simple example. So we have a user service that's trying to embrace async communication. So as you can see, the user service is storing data in Postgres, and that's like its main source of truth. That's where all the user information resides. But the service decides to publish this embrace async communication and publish this over Kafka. This event, user-created event. Do you see any potential problems here? Don't shout. Just raise your hand if you think you know where the problem is. Okay, a couple of people. Good to see that most of you didn't, because well, that's now you will learn. If you all raise your hands, there will be no point for me to be here and tell the things that you know and don't help in reducing entropy at all. So that's the problem, that we have two systems here that are essentially, this is not one system, these are Kafka and Postgres. These are two separate independent systems kind of synchronized by the service and communication over the network. So what's happening in the world of Java mostly is that you have kind of aspects like proxy magic that creates a transaction over a whole method. And guess what? There's first transaction, second transaction. And on paper it looks great because, well, you have transactional annotation here, which makes the whole method transactional. But that won't make your transaction distributed magically. Because guess what can happen now? You persist a user. You save it to a database. And now you try to send the message to Kafka. You send it to Kafka. Kafka says, okay, I received your message. Here is your ACK. And ACK is traveling here back and network dropped. And ACK never reaches the Kafka client here. Kafka client throws an exception. An exception is caught by the transactional aspect and says, okay, there was an exception, we are rolling back. So the event was sent to Kafka, was potentially consumed by other services, but hey, this message, this save into a data, insert to the database is being rolled back. This is permanent inconsistency. You told the whole world that the new user was created, but it wasn't. And that's potentially very dangerous, because that's putting your whole system into a permanent inconsistency state. Because, well, this is maybe just one service listening to it, but what if there's 100? So now, what you would need to do is manually go into all those view models, or inspect how those services, what those services do with this message, and try to undo it. Sounds like hell. So the reason is very simple, that you have distributed transactions, which are hard in the world of distributed system. Some people might tell you that it's quite common when it comes to interviews. I like asking this question in the interview, and some people, when they hear microservices and distributed transactions, they immediately, Saga pattern. I know what you're asking about the Saga pattern. But the Saga pattern won't work here very well. The way the Saga pattern works is that you change one whole big distributed transaction into a series of smaller transactions that can be rolled back. So imagine you want to apply Saga here. So you insert something to a database, but well, you can roll it back. So yeah, you can compensate. You go to insert, delete, okay. But you send something to Kafka message, and how do you unsend a message that was in Kafka, which was already potentially consumed by many services? You can't do that, right? The Saga doesn't work. Then there are a couple of ways you can solve it. One of the old school solutions would be to have a tool that allows you to two-phase commit, which is like the third orchestrator that will actually make sure that this transaction is completed. We will just orchestrate the operations. But this is pretty clunky and requires having a single point of failure, which is usually this orchestrator. And if it doesn't work, the whole system stops working. But the easiest way to solve it, and most pragmatic, is to apply the CDC to the data. So instead of having two independent writes, you have one write to relational database, and then you have a very simple process, which can be as trivial as having a thread with a loop that's checking every second if there are new entries to the database, and then relate it to Kafka. So guess what? This is easy. There's a single transactional insert to the database, and there's a separate process that's spinning forever, essentially trying to make sure that something was sent. Obviously, the network here is unsafe, so it can get dropped as well. But guess what? Then you just retry until success. So obviously you might produce, thousands of millions of duplicates, but you get this guarantees that at some point the message will be here. The same when it comes to delivery. That's also why in the world of distributed systems, you need to start thinking about delivery guarantees, not just consistency, but delivery guarantees. And usually we have two options: at most once or at least once. At most once means, well, I send it once, well, fire and forget. If it arrived, great. If not, nothing happens. At least once means I give you guarantee that you will get my message, but I don't guarantee how many times. It might be once, might be thousands of times. And it's your problem, you need to deal with that. Which is doable. Obviously, this talk is not about that. If you want to discover more about this technique of dealing with distributed transaction of that sort, you want to look at some stuff called Divisium or transactional outbox pattern or chain data capture, and you'll quickly get to some you'll quickly arrive at a couple of potential solutions. Another thing is technologism. So when microservices were getting popular, people would praise the ability of mixing technologies together. So now you are no longer bound by this world of Ruby or Java, but now in the world of microservices you can have Ruby, hold hands with Rust, PHP, Java, whatever you want, right? Because you communicate over network. But the thing is, yes, you can do that, but should you do that? In most cases, no. That sounds great on paper, that you can just mix all the technologies together, but in most cases you end up with a technology zoo that's a pain to maintain. Sounds great on paper, but most companies, I would advise most companies, if I was a developer, I would say, okay, let's throw this Rust, okay, let's have fun, I don't know Rust, let's learn it, I want a new Pokemon for my CV. But if I would be advising a CTO, I would say, okay, dude, in most cases you want to more or less standardize your stack, because you'll be able to move your people easily all around the place. They will know how it works. They won't need to rediscover stuff from scratch. And throw in new tech only when there's really good reason for that. But don't get me wrong, a very good reason for adding new tech might be as trivial as, okay, we want to evaluate this new technology. We want to see if Rust makes sense for our use case. Okay. So we are mostly committed to Java or Ruby, but this service doesn't make sense writing in Rust, but we write it in Rust only to gain competence. Okay, that's also a valid reason. That might be, but then we deal with the fact that we might need to scratch that and go back to Ruby because, well, that didn't work. But that's also okay. But in most cases, if you have more or less the standardized stack, you'll be more happy. And the last thing I'd like to talk to you about, I'm not sure how that's relevant in the world of Ruby, this is especially painful in the world of Java, but that's don't repeat your self-abuse and the problem with shared libraries. And what is it about? So you started with monolith, you have one service. You start embracing monorepos, so now you have 2, 3, 4, 5 services, and you notice that stuff starts to repeat. DTOs start to repeat, dependencies start to repeat, business logic starts to repeat. So there is a user class, the user DTO, in the one of the services, in all the services. Well, don't repeat yourself. Uncle Bob taught us, don't repeat yourself. So let's take this all of that into a separate module that all those services will depend on. And you call it core, engine, utilities, common, or something like common libraries or so. And over time it starts growing. Suddenly someone realizes, okay, you have the same framework in all of those services. Let's put all of those dependencies into core module and make all of those services depend on that core module. And I want to be nice to my colleagues, so let's add a few other versions of that framework, all potential modules, so that we spare our colleagues this really hard work of adding their own dependency to the services. But guess what? If you did slice your services, randomly, not vertically, you might have some overlapping or duplicated business logic. Guess what? Throw it into the common module. And now it becomes really problematic because this common module gets very, very big with a lot of dependencies, a lot of stuff. All the services depend on it. So what usually happens is that you make a very tiny change to that module. Like you bump one dependency, like backfix version. But now you are facing this dilemma. Okay, so I have 200 services that depend on this module. But clearly this really small change couldn't really break anything. So I'm not releasing everything. I'm releasing maybe 1 or 2 services, not 200. Then comes another very small fix that I do to the common library. And I see, so now I need to deploy 200 services. Tell everyone, okay, deploy 200 services at once. No, let's release only those 2 or 3 that really depended on the functionality. So what happens is that there's a huge drift between the state of a common library and what the common library is, the version of the common library that services depend on. And usually what happens is that one day you are forced to migrate to the newer version of a service, you release and everything breaks. This is especially problematic in the world of Java. Java for some reason likes magic. It's a statically compiled language that's statically strong compiled language, but it likes magic. So for example, some libraries, what they like to do is that they will inspect what you have on class path, which is essentially a big ball of all the classes that you have, and they see, okay, you have RabbitMQ connection, like data source object. So if you have this object, you probably want to fire up your client. So they will fire it up for you. But guess what? If you bump your one dependency, which transitively bumps 10 other dependencies, you might want to end up with the fact that this class suddenly is no longer recognizable by the framework. So they don't do their magic. And usually that's super subtle. So for example, easy cases like your metrics stop running. You stop collecting metrics because metrics were collected through proxy black magic. And now this doesn't work because auto configuration based on class path scanning doesn't work. Okay, not bad. But I have a history of my friend that was in a Swiss company working with insurance, and transactional annotation stopped working. Transactional annotation is this part, which is pretty much firing up all the infrastructure needed to ensure that your couple database inserts are done inside the transaction. The transactional annotation was there, everything looked fine, but after a couple of months they realized this data in the database it's not consistent. And they traced it that this transaction didn't work. And that mostly didn't work because of the mess up in the class path, plus with the way how JVM manages transactional annotations in the network. So I'll tell you, if you fire up your JVM and it can't find a class definition that's responsible for annotation, what do you think it does? What would you expect it to do? You start, what you would expect from a decent modern technology to do. So when it starts up, it has a code that's compiled that has references to an annotation, but it doesn't find a definition of the class path. What would you like? Yeah, you blow up, right? Yes, there's something wrong, basically. No, Java actually just ignores that side of it. In the case of annotations, that would be true for classes. If you reference a normal class, you know, and you kind of lost the definition of the class path, well, that would blow up. But annotations are just silently ignored. So the transactional were not really transactional, and yeah, have fun with that. So generally, I would avoid it as much as possible, and because you want to be independent. And if you really want to be safe with a common module, you need to indeed deploy all the services dependent on it. And this effectively brings you back to a situation where you need to deploy everything or nothing. Obviously, it doesn't mean you can't do libraries, but make them narrow focus. Don't put everything in there, and apply best practices you would apply to open source if you were using it. Okay? Because in the bigger companies, you will probably not have all the other teams if they depend on your internal open source. They will probably not upgrade immediately, so like semantic versioning and adhering to not making backward compatible changes is also a good idea. So don't do bags of with code, more like small narrow libraries that can be adopted by some people in the company, potentially not necessarily by your team, and it is another team that you don't control. That means you are doing open source, just companies go. And never business logic in libraries, shared libraries. That's really always a bad idea. Yeah, if you have like infrastructure, some auto configuration for metrics, DTOs or some utils, that's fine. But true business logic usually means that something went wrong when we're splitting services together. There's one more problematic part related to that, but that's mostly Java relevant. So what people tend to do is that when they want to consume, say, a REST API, one of the most convenient ways in Java to do that is to create a user class which has private fields, and Java client and the REST client, most likely by using reflection, will set all those fields for you. So when you call a separate service, you get your object which is ready to go, pretty much. So someone figured out, okay, I have those user DTO classes in a couple of services. Let's put them in a single service. The problem is that Java classes are really bad carrier for contractual data. That's a class that needs to be interpreted by JSON serializing the serializer, and that's how you can more or less use it as a carrier of the contractual data. But this sucks because every service can have different definition of a class. So one service can have your serializer, the serializer that takes a Java class and serializes into a snake case or camel case or something else, or include nodes or no nodes, and so on and so on. So then someone figures out, okay, that can be drift between configurations, so let's share the configuration. And then yet again you have one big module which is owning your serialization, which try to be unified across all the services. So don't do that. I don't know how it's done in Ruby, so I can't really comment. But in most cases, if you want to use if you're using a HTTP client that needs a Java class, you want to have some redundancy. So every service wants to have its own instead of having like shared ones, because Java classes are not good languages for describing HTTP contracts. And that's pretty much all I have for you for today. So let's summarize it quickly. So in most cases, you really don't want to start with microservices. You can always do this. There's always time to migrate. So start with monolith. Ideally, modular is one, and start pulling it apart when you really feel like it's needed. Don't start from scratch. You always have time to do that. You've done this. Congratulations. You are in the world of distributed systems. So those are independent systems. So you can no longer treat them as one. If you do, most likely you will pay a lot of price and not get much value out of that. But guess what? This is not a single system, so multiple systems now. So now you are prone to fallacies of distributed computing. You need to start embracing eventual consistency, because, well, you no longer can be consistent at all times. But again, eventual consistency doesn't mean accidental consistency. So you need to start paying attention to the guarantees that your system provides. At most once, at least once, maybe at most once is not good enough. Maybe you need at least once. And make sure that this is eventual consistency and not accidental consistency, which is very easy to end up with. And finally, add new tech only when there's a very good reason to do so. Just mixing different technologies just because you can usually ends up bad for the whole system. So thank you very much. It was my first time talking to Ruby people. I hope you enjoyed. I hope you learned something. My name is Grzegorz. You can find me on Twitter and on my site. If you want to find the presentation, it's under this QR code, but it will be probably shared with you anyway soon. And that's it. Thank you, and I guess we have some time for questions.